All right, it's 5:19, so let me get started. I was having some adapter issues, so hopefully I can get through this without any problem. So today I'm going to dive into a language that I and my team built. It's a domain-specific language, but it's on the more general side. It's Turing complete, and its usage is for writing on-chain logic on the Cardano blockchain. So just to clarify that, this is not to tell you how to write code using this language. This is to dive into the design and implementation of the language, because I think this is an interesting topic because from a language design perspective, we took some unconventional path to the architecture of the language. And I'm going to explain all the design trade-offs that we had. And I think broadly this is useful because DSLs are quite widespread, and understanding the trade-offs should help you when you need to either design your own language or having to choose one from multiple options. Right. Okay, so just some minimal background first. Like I said, the usage of this language is to write on-chain logic, so it allows you to write any arbitrary logic on the blockchain. And different blockchains have different programming models. So for Cardano, the model is each on-chain program is a pure function that takes user input and transaction data and just returns a Boolean, right? So it's a pure function with no effects. It doesn't perform any effects or actions like transferring assets or things like that. It just returns a bool denoting whether the transaction should be allowed to go through. So this is for transaction validation. Right, so this is the programming model for Cardano, and the pure function makes functional programming a natural choice. So program size and cost matter a great deal. This is the case for, I think, all the blockchains because a blockchain requires a lot of people all over the world to run the blockchain protocol together. That's how you have distributed consensus. So it is a distributed system, but unlike, say, a distributed microservice where you can distribute the workload across all the nodes, for a blockchain, you have to, all the participants have to validate all the transactions and run all the programs. That's how you have distributed consensus, and that's why programs must be small and cheap to run. And that must be factored into the design of the language. And so the on-chain language, which is a compilation target, is something called untyped Plutus core, which is essentially untyped Lambda calculus plus some built-in functions and other simple constructs. And the surface language Plinth is a subset of Haskell syntax compiled via GHC plugin. So GHC is the Haskell compiler. So this is one thing that makes Plinth kind of unconventional because it reuses the Haskell syntax and compiler. So the development really feels like just writing regular Haskell programs. And this leads to a number of benefits, and I'll get more about that later. So, okay, this slide is where okay, apologies for delay, but let me just show this. So this is untyped Plutus core, UPLC. This is the compilation target. It's what this does is this is a program that takes a list of integers and it finds the first integer that is smaller than 10. And this is not designed to be readable, so if you don't understand it, it's okay, because it's a very minimal, very low-level language. There's no data types, and there's no recursion. You can encode recursion using fixed-point operators, but there's no explicit recursion. So because this is a very minimal language, and your low-level language is supposed to be minimal because that's kind of the foundation of everything else. A lot of things depend on it, and mistakes are hard to correct. So this is what Plinth compiles to, right? So this is the surface code Plinth. So this is the same function that compiles to the code in the previous slide. And if you know Haskell, you can recognize that this is just really plain simple Haskell, right? With no bells and whistles. This is just really very simple vanilla Haskell. And this is one of the key considerations that we have. We really want the development of Plinth to feel really like regular Haskell, so that you don't have to learn and adopt a new language or new infrastructure. Like you can just reuse everything that Haskell already provides. Let me try the slideshow here. Okay, still doesn't work. Okay, I think this is still good enough. So now is a good time. So before I dive more into Plinth, let me explain a little bit of like what Plinth, like the entire DSL space and where Plinth sits. So there are essentially three kinds of DSLs, right? So there's standalone DSL, which is new language. And there's embedded DSL, which is embedded in a host language. Like you can embed a DSL in Haskell, which is, it is basically a regular library in Haskell where it allows you to like construct and manipulate ASTs or trees representing expressions, types, and terms, and things like that. There's a third category, which is relatively less common, which is subset of another general purpose language. And this is where Plinth belongs to. It's a relatively uncommon approach, but it can work very well sometimes when it's a good fit. So here are some examples of each category, and the examples on the right are in the specific domain of smart contract languages for Cardano. And so this is a good domain to study the differences and trade-offs, because as you can see, there are at least 2 examples of languages in each category. So Plinth is a subset of Haskell, so it belongs to the third category. In terms of what makes Plinth, so there are a couple of things that makes Plinth interesting, and I'm going to go into details of each one of these. Okay, yeah, I guess it's just not going to work. So first of all, the first aspect is the fact that Plinth is a subset of Haskell. So let me try here. Let me try the slideshow here. Okay. So what does it mean to say that Plinth is a subset of Haskell? It means code is written directly in Haskell syntax, as opposed to the more common embedded DSL or EDSL approach, where you write code where basically it's a new language built on top of Haskell. Like Plinth is not a new language, right? It just reuses a subset of Haskell syntax, as you've seen previously, and the code is also compiled directly. Directly meaning it's just compiled by a modified Haskell compiler, as opposed to embedded DSLs, which again is a regular library. So you first compile that library using Haskell compiler, and then the actual compilation of your DSL happens at runtime. In Plinth, compilation happens directly, just like how you compile a regular Haskell program. And oops, there's a problem again. Oh. Okay, give me one. So yeah, these are some of the supported and unsupported Haskell features in Plinth. So most of the core functional programming features are supported, like algebraic data types, higher order functions, and polymorphism. But some of the more advanced features are not supported, like type families. And this is the first part of the Plinth compilation pipeline. So it essentially reuses the same GHC front end. Again, GHC is the Haskell compiler, right? So it reuses the GHC front end with some small modifications to basically insert some additional metadata like source location, to make error reporting easier. But for the most part, it's just the regular GHC front end. And so the experience is very similar to compiling regular Haskell. So so it reuses the same lexer, parser, and type checker, and everything is the same. And so how does this approach compare to alternatives, right? So like I said, there are 2 alternatives. One is standalone DSL, one is embedded DSL. So for standalone DSLs, there are a couple advantages in that they're highly customizable, right? You don't carry any baggage from any host language, so you can design it however you like. I think that's pretty obvious. But on the other hand, there are some downsides, right? So in general, standalone DSLs are both more difficult to develop and more difficult to learn and use, because in terms of developing, not only do you need to write the whole compiler from scratch, which is already not an easy task, but there's also the problem of establishing a library ecosystem, and if you want any kind of debugger or any kind of testing framework or any kind of meta-programming machinery, you have to do all of this by yourself. And in terms of learning and adopting, there's the problem with scarcity of learning resources, and your experiences in other languages may not be helpful, and the knowledge you learn may not transfer well. And of course, anytime you introduce a new language, a new compiler to your tech stack, there's always additional complexities. So that's standalone DSL. Embedded DSL is more interesting because it bears more similarity with the approach Plinth takes, which is reusing a subset of Haskell, right? Because embedded DSL are also implemented on top of a general purpose language like Haskell. So it's important to understand the difference. So again, embedded DSL, like I said a couple times already, they are just regular libraries. They're nothing special, right? They are regular libraries that provides APIs and functions and constructs for you to construct and manipulate, usually ASTs, representing terms, types, expressions in your language. So they are just a regular library, and because of that, they are also highly customizable, right? Because, for example, if your host language is a functional language like Haskell, and you want your DSL to be an imperative language, that's totally fine. There's no problem whatsoever. And they are relatively easy to develop because it's just a standard, it's just a regular library. And then another advantage, sort of accidental advantage, is that you get metaprogramming for free, because for a EDSL, the compilation, so metaprogramming is basically compile time programming, right? And for your EDSL, let's say it's embedded in Haskell, then the compile time is basically Haskell runtime. So your metaprogramming code is basically just plain vanilla regular Haskell code. And that makes metaprogramming very, very easy. But then the downside is also very significant. The primary downside of EDSLs is that users, there's a lot of cognitive overhead, because users are not writing simple logic using simple types. What users need to do is they need to write code manipulating trees. For example, in the EDSL, you don't get to use the regular int, right? Because that's in your host language. You need to use something like AST of int. And if you want to compare two ints, rather than using the regular comparison operator on the top, you may have to use something like the one on the bottom, which takes two AST of ints and return AST of bool. That's what you need to do. Sometimes you can reuse operator names, but that requires overloading, which is also increases cognitive overhead. And there's also a problem with limited support for pattern matching and branching. Why is that? Well, it's because, say, if you write if then else, the regular if then else syntax, then suppose your EDSL is embedded in Haskell, right? So if you write regular if then else in Haskell, then the branching happens at Haskell runtime. But like I said, Haskell runtime is your DSL's compile time. So there's a mismatch there. So if you want branching in your DSL's runtime, then you have to come up with your own branching operators, which is usually syntactically is worse, and it's a new keyword that the users need to learn. Sometimes the DSL can do clever things to hide these discrepancies. But let me just read a quote from Conor Elliott. He's a programming language researcher. So additional efforts can hide more of these symptoms, but the cracks still show, and each new coping mechanism leads to increasingly mysterious type errors. I think that summarizes very well. So that's EDSLs. And by contrast, Plinth is not a new language or EDSL. It reuses Haskell syntax, plain simple Haskell. So if you want an integer, you just use integer. If you want comparing two integers, you just use a regular comparison operator in Haskell, because it's just a subset of Haskell with a modified compiler, right? So it's easier to learn and adopt. You also learn some transferable skills, right? Because when you learn Plinth, you're basically just learning some simple Haskell, and that's a very useful thing to do in general, right? I mean, if you're not familiar with pure functional programming, then learning some pure functional programming can be very eye-opening. So this is very useful beyond just learning Plinth. But of course, there are downsides, right? Limited applicability is the main one, because now because your DSL is just now a subset of Haskell, so your DSL is much more constrained by what your host language is and does, right? So for example, if your host language is Haskell, a functional language, and you want your DSL to be imperative, then I don't think that's a very good idea. I don't think that works well. And deep integration with GHC, right? This is also a problem. So because you're no longer writing a regular library, right? You need something that you need a modified GHC compiler. So integrating with GHC. So this is usually not very easy to do, because I mean, for some of the languages, their compilers may not even support things like compiler plugins or other ways to integrate with it. GHC does have an API where you can integrate into it, but the problem is like there are just not many people doing that, right? So the API may not be stable, it may not be very user friendly, and it may be missing features that you need. So overall, this is much harder than writing just a regular library. There's also a semantic difference against Haskell. So Haskell is a lazy language, and Plinth is a strict language. And what this means is that some of the good coding patterns and good practices in Haskell are not necessarily good practices for Plinth. I mean, it's not like the result is wrong, but it just may not be as efficient as you like. So these are the downsides of Plinth as a subset of Haskell. So the second aspect, which is related to the first, is the fact that the bulk of the compilation happens in a GHC plugin. I think whenever I try to show one of these slides with animations or images, then it starts to break. But let me try this one. Okay, this is good, but the color is different. It's supposed to be orange. But anyway, so this, what's that? You see? Oh, okay, good. This is the second part of the compilation. So this is where the bulk of the compilation happens. It's a GHC core plugin. So GHC core is the intermediate representation. It's an IR of Haskell used by GHC. And GHC allows you to write this core plugin, which means it's basically an additional pass inserted into the compilation of Haskell, where you take GHC core and then you do some manipulation, you generate some new core, and then the compilation continues. And so this is where it happens. So we take GHC core of your program, and then we compile it into our own IR called PIR, Plutus IR, and then it gets lowered to a language called typed Plutus core, and finally untyped Plutus core. And this untyped Plutus core is then wrapped back into a GHC core expression. So this is like implemented in a core plugin. Okay. All right. So the language that everything else, the core language that everything else revolves around, is called typed Plutus core. So it's a system F omega based calculus, polymorphic, higher order lambda calculus. You don't need to know what it means, but basically it's just UPLC plus types. I mean, there are many reasons why we use this as our core language. Basically, it's very small, it's typed, and it's grounded in extensive academic research. The system F omega was invented about 50 years ago, and there were a lot of research on this topic. And then based on TPLC, we erase the type, which becomes untyped Plutus core, which is the final compilation target that we run in the Cardano node. And then there's also a Plutus IR, which is basically typed Plutus core plus a few things like bindings and data types, which makes it much more readable and suitable as an IR, because it's important for IRs to be readable, because a big part of performance tuning is reading IRs, right, to see how your code is compiled, because it's very hard to predict how your code is compiled unless you, without actually seeing how your code is compiled. And so, okay, this slide is hard to show without animation, so let me try again. Okay, so on the left-hand side, it's Plinth. It's the same any less than 10 function that we've seen before. And on the right-hand side is PIR. And as you can see, this is a fairly readable IR, because there are data types and there are recursions, right? So this is basically a data type followed by a recursive function. So this is fairly readable. And then, okay, good, I'm glad it worked. So this is typed Plutus core, and there's no need to bother reading this, because it's a lower level language and it's very, very much not readable. And then finally, types are erased and becomes UPLC like this. So from here, you can see like why we have to erase types, right? Because otherwise, more than half of the program would be types. Erasing types is the last step, which makes sense, because in early stages of the compilation, types provide assurance that like your optimization doesn't break anything, and then types are erased at the very end. So now again, there are some alternative ways of doing this, right? So GHC. So like I said, how Plinth is compiled is that the bulk of the compilation happens in a GHC plugin, and this is a relatively less common approach, within the already less common category of reusing a subset of another language, right? So perhaps a more common way of compiling a language like Plinth is by the standalone compiler by using GHC as a library, because GHC does publish its own components on Hackage, which is the Haskell package registry, as individual libraries. So it's relatively straightforward to assemble a compiler together by using GHC as a library. So, and this is what some people do. And we didn't take this approach because, so the advantage of having standalone compilers is that, it makes your compiler more first class, right? So now your language has your own compiler. So Plinth may have a compiler called Plinth C or something like that. It's your own compiler. It's first class rather than, having to tweak another compiler to do things that it's not designed to do, right? And you also have more control of the compilation because now it's more modular, right? If you are not happy with the parser, you can easily strip it out and replace it with your own parser. So that's very convenient. But then the downside is that it feels less, it overlaps less with regular Haskell development, right? And I keep coming back to this point is that we really, one of the major considerations we had is that we really want the developer experience of Plinth to just really, really be similar to Haskell. So especially if your team is already using Haskell to do something else, then you don't need to adopt any new language, any new compiler whatsoever. So we just want to minimize that burden and make it everything as close to Haskell as possible. So because we already reused the Haskell syntax, it's just natural that we also reuse the Haskell compiler. So this is the downside of standalone compilers, is that it's a new compiler. And then it's also harder to inspect and manipulate compiled code in Haskell. And this is something that the plugin approach conveniently allows, because the plugin is like, what is a plugin, right? So plugin is basically you insert an additional step in the compiler. And then once your step has been run, the normal compilation continues. And that makes it very easy to mix Plinth code with regular Haskell code, which is very convenient because maybe you want to test your compiled code using some regular Haskell testing library, right? So that makes it very convenient. And to the last point, this is also, there is another important use case for mixing Plinth code with Haskell code is when you need to write parameterized contracts. So you want to compile something, But in your compiled code, you need to use a variable p here that is only, it's maybe some parameters or something that's only available at runtime. So you can't do this, the code in the middle, that doesn't work because that's a stage violation, right? Because your p is needed at compile time, but the p is not known until runtime. So this is a stage violation. So what you can do is instead is this, which is you bind p as p prime in your compiled code. So you compile it as a lambda. And then once you know p at runtime, you lift p into into compiled code. Basically, you serialize. So what lift does is essentially serializing this runtime value into the AST, and then you apply it to your program. And this apply and lift, these are all regular Haskell functions that it runs at Haskell runtime. So doing this requires mixing Plinth code, which is the thing inside compile, with Haskell code, which is the thing outside compile, and the plugin approach conveniently allows this. And there's another alternative, quoted DSLs. This also lets you reuse Haskell syntax. And what this means is, so quoted means metaprogramming using quotations and splices and things like that. So essentially what this does is manipulating ASTs, but instead of using a compiler plugin, you do that using metaprogramming, using quotations. This also lets you reuse host language syntax without any restriction, but the downside is heavy metaprogramming, which is usually not very pleasant because metaprogramming usually it's usually hard to wrap your mind around metaprogramming, like which function is run at which stage, and there's also a lot of syntactic noise and things like that. And the other downside is that it only allows you to work with surface ASTs, which is usually much larger. Remember, Plinth compiler is a GHC core plugin. GHC core is a very small language, but the surface language is much bigger because there's a lot of syntax sugars and there are a lot of different ways to do the same thing. And so, and all of these cases needs to be handled when you do this QDSL. In fact, this is a much more rare approach. I mean, I know that this is a theoretically viable approach, but I'm not aware of any actual production grade DSL that uses this approach. So okay, so this is the syntax, and okay, this is so far I've talked about the syntax and the compilation of Plinth, and the next thing I want to talk about is the runtime. Runtime is the UPLC evaluator. UPLC evaluator is, okay, let me just do a manual animation and remove this. So UPLC evaluator is a highly performance optimized Haskell abstract machine or virtual machine. It's called the CEK machine. And this is interesting to talk about because it is both a very high performant virtual machine and it's implemented in Haskell as a very high level language. So what this shows is that high performance and high level code is not like, they are not contradictory, right? You can indeed write very efficient Haskell as long as you spend a reasonable amount of effort doing performance tuning, but it's certainly possible. So the CEK machine is a virtual machine that is part of the Cardano node. So Cardano node is basically a computer running the Cardano blockchain protocol, and a blockchain requires a lot of people to run this together, right? So each node has this CEK machine inside it, and you can submit transactions to it, and you can submit your UPLC code, and then you tell it your expected cost, and then the node is going to validate the transaction, and part of it is by running the program. And so there are a few different outcomes of running, validating a transaction. It may succeed with the actual cost of the program, and it may fail because the budget has been exceeded, and it may fail because some of the validation conditions are not met, and it may also fail because the machine got stuck. The machine got stuck because is because like there's no translation rule of the machine applies, and that means your program is not well typed, which cannot happen if your program is compiled from Plinth because it's a typed language. But it can happen if you like, for example, modify the UPLC code by hand or compile it from a different language. And an interesting aspect of Cardano is that the script outcome and cost is completely predictable off-chain. And this is important because running a program on-chain costs money, right? So you don't want it to unexpectedly fail, and then you still need to pay for it. And this is achieved by, because you may wonder like how this is possible, right? Surely like the outcome of running a program depends on some kind of on-chain state, like whether you have enough money in your wallet, right? But so how can this be completely predictable? So yeah, I'm running out of time, so I'll go through the rest of the slides very quickly. So the very short answer to this question is that the outcome of validating a transaction itself is not predictable. Your transaction may fail because it's outside of the validity time window, or you may not have enough money in your wallet. But in those cases, your script will not be run. This transaction will be rejected immediately because those conditions failed. The guarantee is that as long as your script is run, is executed, then the outcome must be predictable. So this is a very nice property, which means you will never lose money by running a well-tested script on chain only for it to fail unexpectedly. Just to show you some code of the UPLC evaluator. So this is the bulk of the implementation are contained in two functions: compute CEK and return CEK. So this is compute CEK. It's quite high level, quite readable. I mean, it's actually very close to the actual specification of the language. This is return CEK. So even though we need to squeeze performance out of these programs, the code remains quite high level. In fact, it's so readable, so high level that when other people need to implement their own UPLC evaluators in their own languages, they tell us that they often look at the Haskell code as a source of truth rather than our formal spec, because the formal spec is like more mathematical or more math heavy. And this goes to show you that the code is quite high level and readable. So how exactly do we do this? How exactly do we squeeze performance out of such high level code? Is by using this annotation. So what Haskell allows you to do is using various kind of annotations to influence compiler behavior. So for example, this ban and tilde controls whether something should be lazy or strict. And then this inline, inlineable, no inline, pragmas, there are more like more granular. There are more granular control of the inlining behavior, and then this unpack controls like whether something is whether something is boxed or unboxed, and then you can also have custom classes and instances and types that are more efficient than, in some cases, than the ones provided by the standard library. So you can have all these little tricks. The good thing is that they don't really impact the readability of the code that much, because you're basically just adding a bunch of bans and tildes and inline pragmas here and there. But of course, the process of doing this is not easy, right? Because it involves lots of reading GHC core, because otherwise it's quite hard to predict how exactly your code will compile. Sometimes a particular compiler optimization may fire for a particular piece of code, but it may not fire for another very similar piece of code, and it's very hard to explain. So the only way to know for sure is to read GHC core, which is IR. So that's why IR needs to be readable, because a large part of performance tuning is reading IRs. And fortunately, this is the case for GHC. So this is very feasible for us. And here are some recent numbers from UPLC evaluator benchmarks. And there are various languages, and there's Rust, and there's Scala, C#, Python, and so on. And so far, the Haskell implementation is still the first place. I mean, it's of course I have to admit that some of these implementations are not necessarily aggressively optimized. They are not like for production use in the sense that part of the node validating transactions. They are more for like development purposes. Although I'm pretty sure the Rust implementations, the second and third places, they are fairly well optimized. So this goes to show you the strength of a high-level functional language, particularly Haskell. Okay, so there are 3 more aspects that I wanted to talk about, but I think we're running out of time. So let me just very briefly speak to this. So predicting execution cost is for ensuring higher fair fees and preventing abuse. And there's a systematic way for doing that I was planning to talk about, but because of these interruptions, I think I'm going to skip it. And then compiler optimizations. So the compiler optimizations in the Plinth compilers are also interesting to look at because, especially in comparison with the GHC compiler's own optimizers, because Plinth has very different optimization goals than Haskell itself. So it's interesting to see how we adapt the optimizers based on the different objectives. All right. So for example, for Plinth, the code size matters a lot because there's a strict limit of code size that you can run on chain. So size matters a lot than regular Haskell programs. And there's also a difference between strict and lazy languages. And the last aspect is compiling data types. And there are 3 ways of encoding data types in UPLC. Because UPLC, like I said, is a very minimal language. There's no data type. There's no direct data type support. You have to encode your high-level data type in some way. And there are 3 different ways that we do that, and they each have their own trade-offs as well. Okay, let me skip some of the slides here. So these, if you want to learn more about these, our code is all open source because you can find it in our repository, which has code and plenty of documentation. And you can also look at a paper, an experience report on Plinth that we wrote last year. And I'm gonna show the link at the last slide. So let me just jump to the last slide, the conclusion, learning and observations. So, okay, this is, okay, better. So, reusing Haskell syntax, in our experience, is has pretty compelling trade-offs. By using a GHC plugin, it keeps the development feels really like regular Haskell, which is one of the main objectives that we have. And also, high-level Haskell delivered great production performance. So what didn't work so well, one is that there's a semantic difference between Plinth and Haskell. So you need to adjust. If you're already proficient in Haskell, you may need to adjust some of your habits because developers write. So basically the lazy patterns, the lazy idioms in Haskell may not work so well for Plinth because they may cause your code to be more expensive than it should. But I mean, having said that, this is not as bad as it sounds because for people who write Haskell, where performance matters, they are usually already used to writing strict Haskell, right? Making everything strict because usually that's a more performant way of writing code. And there's also a language extension, Haskell language extension called strict. And if you enable that extension, then everything in your code will be strict. And many code bases do enable that extension. So many people are already writing strict Haskell. And strict Haskell is much more aligned with the syntax of Plinth. And their good coding patterns are also much more similar. And then deep integration with GHC is a challenge. Like I said, GHC API is not very stable and not very complete. And this makes it difficult to, for example, support multiple GHC versions or generating good error messages. And so takeaways, I mean, before building a new language, basically just try to think of basically add this approach to your arsenal, right? So if you previously don't know about this approach of that you can reuse a syntax of another language and then compile it using a compiler plugin, then just add it to your arsenal, right? Because it can be useful. Like I'm not saying you should or should not favor this approach, but your choice should be aligned with your constraints and your goals, right? And each approach has, I mean, these different approaches of doing DSLs, they each have their own very clear trade-offs, pros and cons, like I've explained in this talk. And yeah, just consider what's your goal, what's your objective, and what's your constraints, and align them to your choice of approach. Yeah, high level and fast are not opposites. So if you're willing to profile and tweak your code, you can, and let a mature compiler do its job, then you can have both very high level and very performant code. And this is definitely our experience. I mean, I don't think we had to like structure the code in a way that is very difficult to read or do very low level things. All we need to do is like adding annotations here and there that controls or influences how the compilation, how the optimization is done. And the last point is related to execution cost, which I didn't have time to go through. Basically, if you need to predict the execution cost of your programs, it can be done. You can look at how we do it as a reference. It will certainly limit the language features. For example, one thing it makes it very difficult for us is to support higher order built-in functions. Because if your built-in function can take an arbitrary function as input, and that function can do anything, then like all bets are off. But it only limits to higher order built-in functions. Higher order regular functions are fine, but it will definitely limit your language features somewhat. All right, so so I have some links to, so the top one is our repository, where there's the Plinth language and the compiler and the UPLC evaluator, they are all there. So feel free to take a look. And the second one is the experience report that we mentioned, that we wrote last year. And then the rest is the links to some of the other things that I mentioned in this talk. So, all right. Thank you very much for your time. Enjoy the rest of the conference.